Good morning. Good morning. Myself is Sanjeev Singh. I'm a student of Chemical Engineering Department of MIT Jalandhar. I'm currently studying in the 4th semester. This video is an assignment video on the topic of convection, forced convection and free convection, which we've learned under the guidance of Dr. Shashikant Yadav under the subject of heat transfer. So, in this video we will be discussing the convection phenomenon, basically forced and free convection, and many other topics related to this. So, moving on with the video. In convection phenomenon, what we see is there is a heat transfer between two mediums. Most prominently, these mediums are solid and liquid. So, let us say there is a plate or a solid area and a liquid is flowing above it. So, basically, we are giving the heat to the solid surface, and then this solid surface is transferring that heat to the liquid which is flowing above it. So basically what we see in convection is heat transfer, which is most prominently in solid or liquid. It can be in gas, but we will see in solid and liquid. So it can be external or internal. Like here, this is a plate, solid plate, and fluid is freely moving above it. This is categorized as external flow. This flow is categorized as external flow. Now, there will be a situation where there is a pipe, and in this pipe the fluid is flowing. So, this case is categorized as internal flow. Now, basically what we do is either the heat is given to the liquid or heat is received from the liquid. So, what happens is in convection, fluid is always moving. Point to be noted is fluid is always moving. Now, fluid is always moving. So either the heat is given to the fluid or heat is taken from the fluid. Now, when we give heat to the fluid, what happens is the surface will transfer that heat to the fluid particles that are above it. Now, these fluid particles will receive that energy and their energy level rises. Because of these energy levels, the collisions between them start occurring. Now, there are particles which are actually colliding with each other. Now, due to these collisions, there is molecular momentum transfer. So, what happens is basically the molecular momentum transfer occurs due to this energy transfer. Now we know molecular momentum transfer is basically the definition of conduction. So, convection is having conduction process within itself. So, this is conduction happening in convection. Now, as we are giving heat to the surface and it is transferring that heat to the layer which is above it, what happens is this layer will get excited and the density of this liquid layer decreases because we know the vapor density is less than the liquid. Now, because of the density difference, this layer will go up and the layer which is above this will come downward. So, there is a bulk motion. In various numbers of particles are moving because of the energy transfer. this heat which we are giving to this solid plate, and this solid plate is transferring that heat to the liquid film, there is a bulk motion of these particles which are getting energy. So there is a bulk motion due to energy transfer, which is basically called advection. So advection is nothing but energy transfer due to bulk motion of particles. So convection is nothing but conduction and advection. Now, because of the bulk motion, we can actually classify the convection process into two major parts. So, on the basis of bulk motion, there is free convection or natural convection, or the second part we have forced convection. Now, in free convection, bulk motion is due to density difference, and in forced convection, bulk motion is due to external need. Now, for the convection, we know the governing law is Newton's law of cooling, which is nothing but Q is equal to H A delta T. More specifically, H A, where delta T is Ts minus T infinite. Now, A here is the area of the surface and H is the heat transfer coefficient. So, H is the heat transfer coefficient. Now, H is not a property, but it actually depends on the other factors. So, H depends on the factors such as velocity of the fluid. Now, if the velocity of the fluid is greater or lower, on that the value of H will vary. The second part or the second factor on which H will vary is surface area. So, if the surface is smooth or the surface is rough, that also affects the H. Rather, other than that, direction is also a factor. Like if the fluid is going in this way, breadth-wise, or in this way, the length-wise. In both the direction, the H will be different. So, after that, the orientation can also be a factor. Like if the surface is horizontal or the surface is at an angle to the horizontal, at an angle theta to the horizontal. At last, H will also be affected by the thermophysical properties of the liquid. The next topic which we are going to discuss is thermal boundary layer. To discuss thermal boundary layer, let us first discuss boundary layer. What is boundary layer? Let's say we have a plate. This is a plate, a surface, a solid surface. And let us say there is some fluid which is coming this way with the velocity u infinity. Now, this velocity is this fluid's free stream velocity. What does we mean by free stream velocity? That it isn't under any effect or any other external factor is not affecting this velocity. Each and every layer has same velocity, that is u infinity. It's a free stream velocity and it is not affected by any other external factor. Now, what we will see is when this fluid reach this area where the plate is placed, the bottommost layer or the first layer from the bottom, which is in contact with the plate, this layer will actually stop moving. What is the reason behind that? Actually, there is an adhesive force which is working between this solid plate and this first layer. Now because of this adhesive force, this layer has its velocity has been decreased to 0, to the point that this is now a stationary layer. Now what will happen is this layer will exert a force on the second layer which is above it. Because of that, the velocity of the second layer will get decreased to an extent, not that much but to an extent, because this layer has been stopped and this layer exert viscous force on the second layer. Now because of the viscosity, this will exert a force because of which this layer will the velocity of this layer will get affected. Now what happen will, this second layer will also affect the third layer. Now velocity of this third layer will be affected also because of the viscosity, and so on and so does this goes as is. Now as we move upward, what will happen is the effect of the viscous force will decrease, and there will come a point where the velocity of that layer is as equal to the free stream velocity. Now this curve which we are getting here is velocity profile. Now what will happen is, if we see this at a point which is further away on the x-axis, first this point will be at no motion, this layer is stopped, so this is called no slip condition. So this is no slip condition. Now as we move here, what we will see is, as the fluid is getting more and more on the surface, it is getting more exposed, and there is more exposure and more fluid is in contact with the surface, the force will increase, due to which the effect on second layer will decrease, and so on and so does the effect will decrease by a bit. Because of this, the boundary layer thickness will decrease, and this will become something like this. So boundary layer thickness will decrease and this will become something like this. Now this is delta, or known as boundary layer thickness. So as we move further in x direction, the delta will increase. The boundary layer delta is, now delta is boundary layer thickness. As we move further away in x direction, the delta will increase, and so on and so does. This will happen if we move further. Now, if we connect all these points, we will get a curve something like this. This curve is called the boundary layer curve. This curve is called the boundary layer. Now, we can see so this is the curve which we get. It is boundary layer. Now the fluid can be divided into two parts. The fluid which is under this curve, or fluid which is outside this curve. Now this fluid which is under this curve will have the effect of viscous force, but the fluid which is outside this curve will not have any effect, and the velocity of that fluid will be equal to the free stream velocity. Now as we move upward from the plate to the curve, the effect of the viscous force decreases. As we move upward, the effect of viscous force decreases. So let us say there is velocity u of this layer, and as we move upward, the u approaches to u infinity, and at the boundary layer u is equal to 0.99 times u infinity. So the boundary layer, at boundary layer, velocity of fluid is 0.99 times or 99% of free stream velocity, or as we step just above this boundary layer, the velocity will be as free stream velocity. Now we will see what is thermal boundary layer. Now in thermal boundary layer, what we will see is there is a fluid that is coming toward this surface. In the boundary layer, we discussed about the velocity, that fluid is coming with the velocity something, and how does it affect, and we draw a velocity profile. In thermal boundary layer, we will discuss about the temperature. Let us say the fluid is at a temperature Tf, temperature of fluid, and this surface is at a temperature Tw, temperature of water or temperature of surface. Let us assume that Tw is greater than Tf. Now, when this fluid approaches this surface, what will happen is this first layer, which is in contact with the surface, its temperature will almost become equal to Tw because of the heat transfer. Now, first layer's temperature, the temperature of first layer is almost equal to Tw because of the heat transfer. Now, as we move upward to the second layer, there will be some distance between the second layer and the surface, because of which the heat transfer will be there, but not to an extent that the temperature of second layer will come to Tw. So, the temperature of second layer will be less than Tw. So, as we move upward, the temperature start declining, and so on and so goes. This will look something like this. So this is happen. Now this curve which make is thermal boundary curve. So here comes a point where there is a layer that's temperature is almost equal to Tf. So above that point there will be no heat transfer. Now let us assume same thing on further distance in x-axis. Now let us say here, as we know, the more and more fluid is getting in contact with the surface, so there will be a lot of fluid that will be in contact with surface, and temperature of this fluid will be equal to Tw, and same thing which happens here will be happening here. As there is distance increasing between the layers and the wall, the heat transfer will be decreasing, because of which something like this would happen. So this is heat transfer curve. So what we see is delta T will get increased. Now what is delta T? Delta T is thermal boundary layer. So delta T is thermal boundary thickness. As we move further away in the x-axis, the delta T will increase, that is thermal boundary thickness will increase, and we will get, when we join all these points, a curve something like this, something like hyperbolic. Okay, so now let me define a dimensionless number theta equal to Tw minus Tf upon Tw minus T upon Tw minus Tf. Now here Tw is the temperature of the surface, T is any local temperature. Let us say here temperature is T, so the local temperature will be equal to T. Tw temperature of all and Tf is temperature of fluid. So now let us say this distance is y as we going from the bottom to the thermal boundary curve. Let us say here at Tw the local temperature will be equal to Tw just at above the surface where y is equal to 0. At y is equal to 0, local temperature will be equal to Tw. So at y equal to 0, when we put T is equal to Tw, we will get theta is equal to 0 as Tw minus Tw is 0. Now as we move further away from this, here at y is equal to delta T, we see that local temperature here is equal to the temperature of fluid. So when we put T is equal to T fluid, we will get theta is equal to 1. So the dimensionless numbers value will be 1. So now we will get two parts of the fluid. The fluid which is traveling above this thermal boundary and the fluid which is traveling below this thermal boundary. The heat transfer will be there for the fluid which is traveling below this boundary, but there will be no heat transfer for the fluid which is above this thermal boundary. So this fluid will not get affected by the heat transfer, and the temperature of every layer and every particle of this fluid will be equal to Tf. Temperature at the boundary layer will almost equal to 0.99 times Tf, which is already equal to Tf. So this is how the thermal boundary layer works. Now the next topic which we are going to discuss is dimensional analysis, and in this majorly convection dimensionless number. The first number which we will discuss is Reynolds number. So first number is Reynolds number. So now Reynolds number is nothing but it is the ratio of inertia force to the viscous force. Now getting the formula of Reynolds numbers, from this we know the inertia force is the force that is moving the fluid, the force acting on fluid because of which the fluid is having the motion. So let us say inertial force, let us take it as mass into acceleration. We know that acceleration is velocity upon time, so we can raise it as v upon t. Now mass I can write as rho into volume, which I will write as L cube. Now velocity, now we know that velocity is equal to length upon time. So from this we know time is equal to length upon velocity. Replacing that value here, time is equal to length upon velocity. This will go above, so this will be cut out. So inertial force will be equal to rho L square V square. Now we have the inertial force rho L square V square. Now we will be discussing on viscous force. Now we know stress is equal to force upon area. From this we will get force is equal to stress into area. Comparing it with viscous stress, we will get viscous force equal to nu du by dy into area. Now we know du is nothing but length, so velocity v, and dy is nothing but length, and we can write area as L square. So we will cut the one L out, and this will be viscous force will be nu v L. Now inertial force is rho L square by v square and viscous force is nu v L. So the Reynolds number will come out as rho V square divided by nu VL. Now this will be cut out by this. So what we get is Reynolds number equal to rho VL upon nu. Now it further can be written as VL. The rho which we are having here can go under the nu. So rho VL upon nu upon rho. Now we know nu upon rho is kinematic viscosity. So VL upon nu, which is kinetic viscosity. So this is Reynolds number. Now the second number which we will discuss is Nusselt's number. Now the next number is Nusselt's number. The Nusselt numbers is defined as the ratio of convective heat transfer and conductive heat transfer. We know the convective heat transfer is determined by the governing law of Newton's law of cooling. So it is H A delta T, and conductive heat transfer Q is equal to K A delta T upon delta X. Now this X will go here and these will cut out. So we will have H L by K. So this is Nusselt's number. Now the next number which we will discuss is Stanton's number. Now Stanton's number is defined as the ratio of convective heat flux and heat capacity of fluid. We know that heat transfer because of convection is, and convective heat flux is nothing but heat transfer is given by unit surface area. So we will divide it by the area and we will get H delta T only. So convective heat flux will be equal to H delta T. Now heat capacity for fluid is mCp, and we will multiply it with delta T because we are taking the temperature of per unit area in. So it will be written as H delta T will be also cut out. It will be H upon mCp. Now I can write m as rho into V. So this will be H upon rho V Cp. So this was Stanton's number. Now the next number which we will discuss is Prandtl's number. Now the Prandtl's number is known as the ratio of kinetic viscosity to the thermal diffusivity. We know that kinetic viscosity is nu and thermal diffusivity is alpha. It is written as nu upon rho and it is written as K upon rho Cp. Now this will go above and it will be rho Cp upon K. We will cut out the rho and we will have mu Cp upon K. So this is Prandtl's number. Now, the next topic which we discuss is Buckingham's pi theorem. Buckingham's pi theorem states that efficiency of a fan depends on rho density, nu dynamic viscosity, W which is angular velocity, d which is diameter, and q which is discharge. Now, efficiency of a fan, that is eta, depends on these factors: density, dynamic viscosity, angular velocity, diameter, and discharge. So we can say that eta is a function of rho, nu, w, d, and q. Now, eta is a dependable variable. On the other hand, these are independent variable. So, variable now finding a functional relationship between dependable and independent variable, that is f1 of eta rho nu w d q equal to 0. This is a functional relationship between dependent and independent variable. Now, total number of variable, which is denoted by n, is equal to 6 here. 1, 2, 3, 4, 5, 6. Now, the total number of variable is n is equal to 6. Now, finding the dimensions of these, first, density is mass upon volume. Mass is nothing, kg, and volume is m cube. So it is kg, which is m, and L minus 3. So now dimension of nu, which is n as m square, nothing but kg. Now Newton is force, that is mass into acceleration, that is this upon m upon s square into s into m. This will be cut out and we will be left with kg upon s, which is m and t minus 1. Now the angular viscosity, which is radian per time. So this will be nothing but t minus 1. Now diameter, which is L minus 1, and discharge we know is AV. A is m square, V is m upon t. So this will be L cube t minus 1. So these are the dimensions. Now fundamental dimensions we have here is denoted by m, which is equal to 3. Now what Buckingham Pi's theorem state is number of pi terms will be equal to n minus m. So here we had n is equal to 6 and m is equal to 3. So number of pi terms will be 3, which is pi 1, pi 2, pi 3, and we will get a function pi 1, f1, pi 1, comma pi 2, comma pi 3 equal to 0. Now using geometric property, flow property and fluid property, writing pi 1, pi 2 and pi 3, these will be the values of pi 1, pi 2 and pi 3, and this was the Buckingham's pi theorem. Now we can put this value into the function of f1, which is pi 1, pi 2, pi 3, and solve it further, and the function will be satisfied. So this was the topic of Buckingham's pi theorem. Now the next topic we are going to discuss is free convection. Free convection is always due to density difference. It is convection but just due to density difference. Now what happens is, let's take there is a surface on which there is some fluid. Now what happens is we are giving heat to this surface. Now when we give heat to this surface, these particles that are in contact with the surface will get heated. These will absorb this heat and they will convert into vapors. Now because these particles have a higher temperature than the above layers, we know at higher temperature the density of vapor is less than the density of liquid. So these particles have slugs of vapor in them. Because of that, they have a higher temperature and their density declines. Now because of this, there is an upward thrust on these particles due to the density difference. That is why these particles are going upwards, buoyancy force is acting, and these particles are coming downward, which has higher density. So this convection which is occurring naturally, free convection is also called natural convection. This convection which is occurring naturally without any external means, just because of the density difference, this convection is called free convection. Now let's take free convection example in an open surface like this plate. Let's say there is a plate, this, and because of this we are going to see free convection. Now in forced convection we know there is boundary formed, boundary layer, and don't have to do anything. Now in that matter we don't take generally gravity force, but gravity force is very important concept in free convection. We will take gravity accountable when we are discussing the convection in free convection. Now let us say we maintain this wall at a temperature Tw, which is constant temperature for the wall, and this is the temperature of the ambient, T infinite. Now what will happen is the air here will be at a greater temperature than the ambient, that is T is greater than T infinity. Now as air is at a greater temperature and is in contact with wall, that air will get heated, and because that air is getting heated now, its density will become lower, and what that air will do is it will go upward and we will obtain a boundary layer something like this. So here at this point temperature of the air is greater than the ambient temperature. Now the velocity of the particles here and here will be 0 because it have to be in this position. So particles will move from here to here, but velocity at this point and this point will be 0. So what will be the velocity profile will look like? It will be something like this. The highest velocity will be achieved at a point C, which will be between these two. So this will be the velocity profile due to a simple plate. Now after this we are going to discuss a cylinder. In forced convection we discussed the cylinder, and what we did was a fluid was coming and this was happening because of the forced convection. There was this boundary layer and there was then this separation and this current, and this will look something like this. Now what happened in free convection is, this is the hot surface, this is the hot surface. Now when a cool air is getting in contact with this, something like this will happen. The buoyancy force is acting up. Now as air gets contacted this hot surface, its density decreases, due to which it moves upward and buoyancy force is acting. So this will be the flow in free convection due to a cylinder, and as we discussed, this was the forced convection flow. So this was free convection due to a plate and a cylinder and free convection phenomenon. Thank you very much. The next topic which we are going to discuss is external and internal flow. First we have external flow. External flow is mainly due to the submerged bodies, like one we here have. This is the submerged body and water is flowing around it. These are the layers of the water. Now the most important concept in external flow is boundary region or the boundary flow. What happens is this region, which is just outside the body, is known as the boundary region. Now this region is known as the boundary region. Now this is a submerged body and liquid is flowing through around it, and this is the boundary region. We have already discussed this before in boundary layers, and this is what happening. What we discussed before was there was a plate, and we discussed the external from this, that a fluid was coming, and then what happened was the velocity of the fluid was u infinity, that is the free streamline velocity, and the bottom layer stuck here because of the no slip position, and what we did was we formed a velocity profile. So on and so does we found the delta and we calculated it. These are some other examples of external flow. We can take a cylinder and there is fluid which is flowing with streamline, free streamline velocity, and the flow around this cylinder would be something like this. Now this, the region just outside the body, is the boundary layer. This is known as boundary layer. Now this is the separation. This is the separation of fluid from the body of the cylinder. This can be the diameter, and this is how an external flow is due to a cylinder. This is external flow due to plate, and there is one submerged body. Now the next part which we are going to discuss is internal flow. We have already discussed that if there is a surface and fluid is coming towards it, what happens? Something like this, a boundary layer will be formed. We have discussed it in velocity as well as in temperature. Now let us say if the fluid is flowing through a pipe. So what will happen is the boundary layer will be formed from this side, and the boundary layer will be formed from this side, and there will come a point where these two layers will join together and the streamline will continue. Now we know if we take this part, the temperature below this part will be T local, and above this part will be T infinity or T saturation. And now same with this, there is a T local. Now the only part where T infinity was beyond this. Now from onward this part, there will be no such point where the temperature should be T infinity or temperature of fluid, which will be known as free temperature. So here let's say temperature is T mean meaning average temperature. So the heat transfer after this region will work as we know for convection the heat transfer is Q H A delta T, where delta T is T W minus T infinity. So now this is the temperature at any layer which we are getting Tm. So this T infinity will be replaced by Tm and the heat transfer will change to this. So the heat transfer with T infinity will not be possible after this point. So what will happen after this point is a fully developed flow will form like this. From this there is this plane flow. What we see here is something like this. But after these two streamlines submerged into each other, what we see is a fully developed flow. So the region onward this is a fully developed flow, and the region behind it is hydrodynamic access region. It is an hydrodynamic entrance for the fluid. So this is how the internal flow works, where heat transfer will actually not equal to the original heat transfer. It will change, and for the T infinity we will take the Tm part. The next topic which we are going to discuss is laminar and turbulent flow. Let's say we have a pipe. This is the pipe and we are going to flow of liquid through this. Let's say this is the fluid which is coming, this is the in and this is out. This is from fluid is getting out. Now let's say this fluid has these small particles or layers which have their velocity v. Now in laminar flow what will happen is, if these layers are gliding smoothly over if the adjacent layers are gliding smoothly over each other, or we can say all the particles are following a guided path, or they are following a streamline. A streamline is something like this, a parallel line in which all the particles are flowing with same velocity. This flow is known as laminar flow. This flow is known as laminar flow. Now, on the other hand, turbulent flow, let's say we again took a pipe in which this is from where liquid gets in and this is where from it gets out. Let's say there are particles of the fluid, but they have a random velocity. Particles are moving in zigzag formations. Now, because of this, there will be a highly energy loss, because as they will move in zigzag position, they will collide with each other. As they will collide with each other, there will be energy momentum transfer, because of which there will be high energy loss, and even there could be eddies formation. Now, when the particles do not follow the streamlines, or they do not follow the guided path, or they go in zigzag position, this flow is known as the turbulent flow. We can also define laminar and turbulent flow with Reynolds number, which we have discussed earlier. Reynolds number was the ratio of inertial force to the viscous force. Now, if the Reynolds number is less than 2000, the flow is known as laminar flow, and if the Reynolds number is greater than 4000, the flow is known as turbulent flow. So this was the laminar and turbulent flow.